everyone, my name is Amanda Jenkins, and today I'll be discussing mass spectrometry and infrared spectroscopy as it relates to 2-methylpropene. As you can see here on the right, this is our molecular structure for 2-methylpropene. It has a molecular formula of carbon 4, hydrogen 8. Um, and we'll be using mass spectrum and infrared spectroscopy to get a better understanding of how we use these tools in order to identify unknown compounds that we need identifying. Okay. Hello, everyone. My name is Amanda Jenkins, and today I will be presenting mass spectrometry and infrared spectroscopy as it relates to 2-methylpropene. As you can see here on the right, this is our 2-methylpropene structure. It has a molecular formula of C4H8. And we use mass spectrum and infrared spectroscopy to get a better idea of the structure of the molecule and identify unknown compounds. So mass spectrum identifies the mass to charge ions of molecules against their frequency and intensity. So we're able to identify things like molecular weight and the structure based on the common fragments that are identified within the molecule. Many molecules will fragment in the same sort of way, so we can really have a better understanding about how they fragment and be able to build a structure based off of those fragments. Infrared spectroscopy measures how molecules interact with infrared radiation. This allows us to identify their functional groups, and it works better with simple molecules just because as you get more complex, it sorts to overlap. So it's better for simple molecules, but using these in conjunction can give us a really clear understanding of the structure we're working with. Um, so as you can see here from the mass spectrum, it has a molecular mass of 56 AMU. This is identified based on the molecular peak ion, which is that ion right there at the end, and is the full molecule that we're working with. We also have a spike at 41, which is going to be our base peak or the most abundant ion. So this is our most common fragment observed within the mass spectrum. And you can see that here on the left, major fragments being having an MZ of 41, and it'll fragment and produce a carbon bonded to two other carbons with 5 hydrogen respectively in that double bond. And it'll also produce a minor fragment of carbon with uh, 3 hydrogens. But that's less apparent on our mass spectrum, the main fragment being the 41 one. And if we go back here, we can see where this structure actually fragments. It will fracture along these single bonded carbon lines, and it'll do this because whenever it creates a fragment, it wants to create the most stable fragment that it can, and it does that by creating tertiary carbons, and so that's where it's most likely going to fragment is along those really strongly bonded carbons to produce more stable carbons rather than one that's a primary or one that's a secondary. And it's also not likely to fragment along that double bond because that double bond is stronger than the single bond, so it's easier to break those single bonds than those double bonds. So it's going to fragment along these single bonds um, most likely, and there's not a lot of carbons we're working with here, so it's really not going to fragment any other way, which is why we only have a few fragments to work with. If we move on to infrared spectrum, however, we can see the IR frequencies based on this graph. I identified some major areas where it was spiking in a relative transmissions. Um, so we see around 900 to 800 centimeters. We kind of get this uh, carbon double bonded the hydrogen bending, and that's going to be your in and out of plane bending that occurs when molecules are conflicting with each other. And we're also going to see from 1700 to 1600. It's going to be a little bit lower because they're not as strong, but you'll see that your carbon double bonds stretching against each other. And then that 3000 to 2900 is going to be your carbon double bonded hydrogens stretching. So we can identify that this is an alkene based on um, what we've identified, the multiple, some of them overlap, which is why we have problems with things that are much more complex, but the more that you kind of reduce those molecules, this paints a very clear picture that the molecule we're working with, because all of these have been identified, that the molecule we're working with is an alkene, and we know that based off the fact that that was what we put in. So 2-methylpropene is an alkene, so that is the functional group that we can identify. And um, thank you for watching. I hope that you have a better understanding of mass spectrum and infrared spectroscopy. Thank you.